Okay, so now basically this is apparent magnitude. Notice that it's the little m. We're going to have a big M, a little m. This is the apparent magnitude. And the apparent magnitude is just a way to take the apparent brightness and map it onto a logarithmic scale. And apparently the problem is that, of course, the watts per square meter vary over such a giant range of watts per square meter our eyes can see, actually, right? And so what we do is we actually make it into a logarithmic scale. Now, this is very strange because normally you'd think that you'd put the brightness in the numerator, but they put it in the denominator, and what that does is it makes small things, it makes small m's big brightnesses. It's like a reverse scale. This is a weird thing, and I'm very sorry about this. But I didn't invent the scale, but it's the one that everybody uses. Okay, so a star that's like a -1 is really bright, and a 4 is very faint. Okay, and I'm very sorry for this, right? Notice that it's got a number, sort of an arbitrary constant built in there. Obviously, if you have a brightness equal to that, right, then your magnitude is, the log of 1 would be 0, right? You raise 10 to the 0th power to get 1. And so 0 is just sort of a star. If you have that same brightness, then you'll have an M of 0, right? And the rule for this scale is that if you multiply your brightness by 100, you go down on the scale by 5, right? So if you have a magnitude 6 star, a magnitude 1 star is 100 times brighter than it, and a magnitude -4 star, right, would be 100 times brighter than that, right? Every 5 that you go up, or down, sorry, every 5 that you go down, you go up in brightness by a factor of 100. So it's just the strangest thing. Okay, let me help you wrap your mind around this. I'm going to do an example. Actually, I'm going to go to these things, and then we'll do an example, right? So here's the sun. The sun is like -26.8, right? The moon, the full moon is -12.6. So that's, besides the sun, of course, the full moon is the brightest object in the sky. The moon is actually painful. If you've got a big telescope, it is pretty blinding to look at. The best time to look at the moon actually is when it's like a little crescent, and then you look at the shadow edges, and it casts a good relief on the craters. -4.4 is Venus, and then Mars, and then the brightest star in the sky is, of course, Sirius. And I've already told you that it's seriously bright, right? I would talk about this star here, but that's a whole nother can of peas. Okay, don't want to talk about that, right? And then you can see with a naked eye +6s, right? A quasar is a distance galaxy, and so those are very, very faint. Pluto's you need a good telescope to see Pluto, right? Kitt Peak, our national observatory, can see down to there. And then I love this. This is my book from the 70s or something like that, right? With the space telescope when it is launched, right? Jay knew that it would be a good thing, right? Okay, and so just remember, -27 is, it's going to burn your eyes out. 1 is kind of a normal bright star, and then 6 is something that's barely visible to a naked or unclothed eye. But then, of course, if you clothe your eyes, you can't see anything, right? And then just remember that a magnitude 1 star delivers 100 times more watts per meter than a magnitude 6, right? And a magnitude 11 star would be 100 times fainter than a magnitude 6. So let's go back to our example. Okay, what is the apparent magnitude of a star with an apparent brightness of 7.2 times 10 to the -10th watts per square meter? What is that of a star with an apparent brightness of 7.2 times 10 to the -12th? Well, what is our formula? I think, what is it? Let's see if I can remember. M is equal to 2.5 log base 10 of 2.52 times 10 to the -8th watts per square meter. We'll find out real soon if I've got it right. Okay, divided by our brightness, right? Okay, so I can go ahead and just stuff these numbers in, right? 2.5 log 10 of 2.52 times 10 to the -8th watts per square meter. And then that's divided by, let's divide it by this first brightness here. So 7.2 times 10 to the minus 10th per square meter. Ta-da. Okay, so let's do that. 2.5 times log. I always say times even though I don't have to. Parenthesis 2.52 e minus 8 divided by 7.2 e minus 10. Right parenthesis. Hey, I got it right. That's 3.86. 86. And there are no units to this, right? There's no units on this. This is watts per square meter over watts per square meter, right? I think that's kind of a rule. If you're going to take the log or the sine of something, whatever you're taking the log or sine of doesn't have units. These all cancel, right? So that's the magnitude, right? So it's we can see down to a 6. We could see this star, right? So let's do the other one. That's 2.5 log 10 of 2.52, 10 to the minus 8th, right? Divided by, and then this one's 7.2 times 10 to the minus 12th watts per square meter. Now we made a prediction of this, right? This star here is 100 times fainter than this star, right? So it should be 5 more than this. When we plug this into our calculator, we should get not 5 times that, but 5 more. So 8.86 is what we should get. I'm too lazy to type it all in, so I go second entry. I go back, I change the minus 10th in my previous thing that I typed into the calculator to a minus 12. And I'm getting 8.86. So the world is a good place. Okay, and again, there are no units, right? With 2 sig figs, it would be that. And then the final thing that's kind of cool is that amateur astronomers, there are certain key stars that everybody knows. I don't know them, but some people do, right? And they know that that star there is a, you know, a 1, and this star here is a 3, and that one might be a 2, and this guy here might be a 6 or something like that, right? Okay, and what people can do is they know those stars, and they can actually guess. There are amateur astronomers that can guess the brightness of a star down to a 1/10 of a magnitude accurately every time. And you could too if you practiced. I don't know, do I have another example? I don't think so. Oh, here's another example. You don't have to do this one, but I'm gonna what is the apparent magnitude? I'm gonna do this one. I'll bust this one up. You don't have to do this, but I'm gonna do it. Okay, so let's see. Apparent magnitude, little m, is 2.5 log 10 of 2.52 times 10 to the minus 8th watts per square meter. Oops, gotta do the whole parenthesis. Okay, and then this one's 1.4. All right, and then I'm just going to go second entry. I've got it all typed in here, so I'm going to go 1.4 e to the minus 9. Then I got to hit delete, and I get 3.1338, right, which would be 3.1 with a couple sig figs. Do I have any more? Oh, there we go. What's the apparent brightness? Okay, so we got to be able to go in there and solve for the b. So little m is 2.5 log 10 of, I'm just going to say b naught divided by b, right? And I'm going to say b naught is equal to 2.52 10 to the minus 8th, okay? Because I don't want to do math with all that number that's hard to write down. Okay, so little m divided by 2.5, 10 raised to that is equal to b naught over b. Okay, so let's see, we're trying to solve for b, right? So b, let's see, b is equal to b naught times 10 to the minus m over 2.5, right? Is that right? I think that is right. I do believe so. So what I've done here is I put this guy in the numerator, and then I put this guy and put it in the denominator. Over there, I switched this term and this term. Doesn't look like it, but I did. Okay, so 2.52 10 to the minus 8th times 10 to the, what is it, 28? The minus 28 divided by 2.5. That's supposed to be 10 raised to the power. 10 raised to the, okay, let's try that. So let's go 2.52 e to the minus 8th times 10 raised to the negative 28 divided by 2.5. Boy, I sure hope this is the right answer. 1.59 times 10 to the minus 19th. And that, of course, is watts per square meter. How is it watts? Oh, because this guy is watts per square meter. This has no units, and so there we go. I guess with 2 sig figs, we'd have to say that. Huh? Apparent magnitude, not so bad, is it? Do you have any more? No, we don't. All right.